So thanks for coming, everyone. Nice to see so many familiar faces. So I guess this is some of the work from my honours project last year. And the project was sponsored by the company which I now work for, Gold Road Resources. Huge, obviously, thank you to them, colleagues in the room tonight. And also, I should acknowledge our supervisors, Professor Tony Kemp, fantastic geochemist, and Dr. Elena Belasova from the GSQ. And subsequently, after finishing my project, this work's really been improved by some input from Greg Morrison, who's the IRG kind of expert. So the title of my talk is Accessory Mineral Indicators of Metallogenic Fertility for IRGs, which stands for Intrusion-Related Gold Systems. It's a bit of a mouthful, but we'll go through each of these kind of terms now. So intrusion-related gold systems, what are they? Well, there's a schematic model of them here. This is some work with Tim Baker. Really shows the kind of variability of these systems and the different kind of textures you get. All kind of fit under the banner of IRGs. The definition that I've come together with is these kind of variable classes of magmatic-hydrothermal mineralizing systems. The mineralization is undoubtedly hydrothermal, but there's a direct, or I guess demonstrable, link between the mineralization and igneous source. So you get the idea that the magmas are really carrying our metal budget in this. And typically they're Phanerozoic, or the ones we think of when we talk about IRGs are Phanerozoic. There's also Proterozoic and Archean examples, but we'll kind of not really focus on those today. Okay, so where can we find them? Well, it's pretty easy. You find them inboard of subduction zones, and I guess the birthplaces of IRG term classifications. Up in the top corner there, the Tintina in Alaska and the Yukon. This is kind of where we first discovered these systems and where we first found that they were actually worth exploring for. And there's also a belt of them across the closure of the Paleotethys through Europe and Asia there. And there's another one down the east coast of Australia in the Tasmanides. And that's where we're going to focus for this talk. And also these things kind of hang around in provinces that are known for tin and tungsten mineralisation. So that's an interesting, I guess, observation. Right, so let's have a look at some of them. There's a grade tonnage plot here from Craig Hart. This really, I guess, demonstrates the variability in these systems. You get these really high-grade, low tonnage ones, it's typically associated with skarns. Some beautiful examples here, sulfide assemblage and andradite garnets. This is from Red Dome, which is a deposit in Queensland. And again, these are really like spectacular grades, but quite small systems. The typical Yukon system looks something like this, which is a sheeted vein array. You can see these beautiful parallel veins outcropping on the side of a hill there. Now, these are quite high grade and also quite large tonnage. So these are really what we're after. I guess these represent a bit more of the kind of end-member examples of what an IRG is. And finally, we've got the intrusion-hosted deposits, which are by far the most common. And they're our classic, like, low-grade, high-tonnage things that are typically hosted in really fractionated portions of the cupolars of composite intrusions. And we can see beautiful banded arsenopyrite here. And this is an example from Dublin Gulch in the Yukon. Right, so focusing in on Queensland and Eastern Australia, this is a typical schematic put together by Greg Morrison that highlights the variability of IRGs and focus on Eastern Australia. And typically, I guess the definitions that we're used to for these intrusion-related gold systems come from the Yukon. But the Eastern Australian examples really kind of stray away from that in the most stringent terms. In that they're typically hosted in breccias, at least the big ones are. And also they're not low sulfide. So you can see beautiful sulfide textures here from a sheeted vein at Kidston, and also a massive sulfide vein from Okay, so this is where the metallogenic aspect of I mentioned that these are magmatic systems, the ores, or at least the metals are transported within the magnets. And this really opens the scope to magmatic investigation into processes which make these things fertile. And there are certain magmatic conditions which promote either gold concentration or gold transport. And I guess uncovering what they are is kind of the focus of my research. So we know from a lot of work in kind of the porphyry copper world that gold is easily transported or best transported in oxidizing magnets. In the oxidation delays the onset of sulfide crystallisation and preserves the chalcophile element budget of your magnets. We also know from a very interesting paper done on an intrusion-related gold system, the Timbara system in New South Wales by Roger Mustard and colleagues, that perhaps we don't even need a gold source to these systems. The fractionated magmas themselves can actually concentrate gold to economic conditions without the need for a pre-enriched source. Now, the caveat here is he says that under permissible conditions, which it doesn't actually specify what they are. And the answer is because we don't know, which is very, very fair. But if we can find these conditions, perhaps we can find more IRGs. And for any of this work to actually mean anything, you really have to have a very well-constrained relationship between the magma and the mineralisation. So if we're working in a deposit with multiple magma generations, we really need to know which one brings in the ore. Unfortunately, at Mount Leyshon, that's actually really well constrained. Okay, so one of the last terms in my title was accessory minerals. I'm sure most of the people in the room are familiar with these. Zircon's familiar probably to most. It's a zirconium orthosilicate. It's really useful because it saturates early in magnets, and it's really robust. So often, at least in young rocks, it's not particularly altered and it doesn't get weathered easily. It's also very useful because it hosts things that we can, I guess, probe into the petrogenetic history of our magmas, things like the rare earths, hafnium and titanium, and also isotopic. I guess it's a good isotopic host for things like hafnium and oxygen. Apatite's a different one. Apatite's calcium phosphate. It's this beautiful green crystal here. And again, often saturates quite early. The downside to apatite, though, is it's a little bit less robust and it's prone to alteration. I guess more prone than zircon would be. But the real upside of apatite is it can track our volatiles. You can see in the formula there, it can accommodate things like fluorine and chlorine, which can be used to assess the magmatic volatile budget. And that's a real upside. And also it hosts useful isotopic systems, things like strontium and neodymium. And I guess from all of that, the overall thing that accessory minerals are great for is recording the magma. And the magmatic conditions we know is critical to producing a gold fertile melt. So therefore, it's a logical link that we look at these things to try and predict fertility. So how do we do that? And that's through the analysis of these minerals. These are examples of apatite and perfect zircon that someone shot a hole in with the laser. And this is, I guess, the techniques that I did. So looked at some whole rock geochemistry, also characterised the apatites and EPMA, which stands for electron probe microanalysis, and laser ablation, inductively coupled plasma mass spectrometry for the trace elements in both minerals and also uranium-lead geochron in the zircons. So finally, what are fertility indicators? Well, when I started the project, I really didn't know, but I had seen this diagram before. This is the mineral systems model from Clay-Gronsky, and fertility is one pillar of that. Now, the best definition I can come up with for what fertility indicators are these sets of chemical and isotopic proxies for processes. But the critical thing is that these processes must be linked to an increase in the potential for mineralisation. And that's nice, that sounds good. But what's the deal? Well, it's actually quite difficult to do this, particularly understanding which processes are linked to fertility and which aren't. Now, you can visualise a lot of processes through this technique, but understanding which ones are critical and which ones perhaps have no effect is a lot more difficult. Also, we need to understand what the samples are, what the data is representing. So if our samples are altered or fractionated, perhaps some of the trends we're seeing is because of these factors. And finally, we don't know what fertility indicators are for IRGs, unlike the wealth of knowledge for porphyry copper systems. And finally, this is where the permissive conditions come into it, is that these are really the conditions that we're trying to, I guess, uncover with what they are. So then we can go and use this in terms of furthering our exploration for these systems. Enough spiel. Let's have a look at some of my research. So what I set out to do was investigate these accessory minerals in two different magmas. One of them was gold fertile magma, which in our case was the Mount Leyshon intrusion-related gold system, which sits down here in Charles Towers. And we wanted to compare that to a tin fertile system to see if we could spot any differences. The tin fertile magma was the Hermiton Hill Range there, just west of the Cairns. And we tried to sample igneous lithologies to retrieve apatite and zircon. So some of the questions that I was trying to answer, first of all, is what can these accessory minerals tell us about the magmas that produce gold and the magmas that produce tin? And the answer to that will be revealed. And the next question, I guess one step above, is can we develop fertility indicators for these systems based on the analyses of these minerals? Sorry. And the answer to that is yeah, I reckon we can. But just an investigation in one system kind of isn't convincing enough, right? I guess the overall question is shown in the photos is can these guys, these apatite and zircon, can they point us towards the mineralisation? And I think we're well on the way to developing that. Okay, so Mount Leyshon, this is a map of it. It's this breccia-hosted IRGS, which is situated in the Charles Towers province. The mineralisation style is gold, bismuth, silver. And, it's about 3,500 ounces, so it's pretty significant, and sits right on the contact, or right on the boundary, sorry, between the Permian and the Carboniferous. That's it in map view, and this is it in cross section. And this is one of Greg Morrison's cross sections. And I guess the thing to gain from this is that it's a really dynamic system. We have three individual pulses of magma, each with their associated mineralisation. And one of the most critical paradigmatic relationships from this deposit is that the gold is the last pulse. It's associated with the very last magmatic event, and it comes through and mineralises the entire system. So if we have a look at the magmas, this kind of threw me for a loop, because I was only kind of introduced to this idea recently, is that Mount Leyshon is actually reversely zoned in terms of the magmatic evolution, in that the initial pulse of magma is this most fractionated rhyolite in the entire system, and it gets less and less fractionated, less and less felsic as this thing evolves. Although an interesting, I guess, feature is, okay, within each pulse of magma, there's a normal progression. It's fractionated, it evolves through crystal fractionation. So within an individual magma, you have a mafic fringe, and it gets more and more felsic towards the core. So in that sense, it kind of evolves normally, but the entire complex is reversely zoned, which is a curiosity. And to the best of my knowledge, Mount Leyshon is the only IRG, at least in East Australia, where this is the case. Okay, so I'll briefly rip through some of the rocks. We have a graphic log, a hand sample photo, and also a photomicrograph. These are some of the basement lithologies, so these magmas aren't Permian, and they're not involved in the mineralising system. The pretty standard granite. There's also a porphyritic version, these beautiful euhedral quartz things. And all of this is cross-cut by this later kind of diorite, the dolerite dikes, superhydrous things full of hornblende and light. In terms of the Permian magnetism, this is, I guess, the first pulse. This is really fractionated and felsic metal. It's weakly porphyritic, but the phenocrysts are pretty scattered. You can see a beautiful feldspar there that's ringed by these albite spherules. Quite an interesting texture. This is the southern porphyry, which is the most, I guess, volumetrically significant pulse of magma. Again, pretty similar in composition, feldspar phenos and these albite spherules, but also we have quartz now. This displays this like sieve texture. And finally, the gold mineralising event is discovered, which is the late diet. And this is a bit distinct because now we have biotite phenos. We don't see in any of the other magmas. Again, beautiful resorbed and sieve textured quartz, and even the feldspars they're looking all right. For the amount of alteration that's happened in this system, these are pretty pristine. Actually, this thin section was the least altered sample in the entire state, believe it or not. And finally, the good stuff, this is the ore textures. you can see these beautiful geometric sulfide infills within these breccia cavities, and as soon as this thing hits a cavern, it produces these beautiful euhedral pyrites. So the majority of the ore is hosted in breccia, and the rest of it is in veins. And these veins overprint mineralised breccia, so they're kind of the last pulse. And again, when these things hit a cavity, they produce nice euhedral quartz. Okay, so that's enough of the introduction. Now let's have a look at the good stuff, the microchemistry of these accessory minerals. And this is our apatite. So for those unfamiliar with apatite, it should look like that row on the top. We can see beautiful magmatic zoning in the first one, facilitary zoning, sorry, and sector zoning, and also there's a little homogeneous one up there. But the rest is just above ground, like these kind of, I don't know, you call them leopard print, spotty, I don't know. But this one, I guess you could kind of be convinced that that's some form of magmatic zoning. But yeah, it's just don't know what's going on here. So because we didn't know what was happening and what was causing it, we investigated it a bit further and took it to the EDS. And these are some really high resolution BSE images, backscatter images of our apatite. And the first thing you'll notice is it's full of holes, which isn't a great sign. And it's also full of these little BSE bright mineral inclusions. Now, when we analyse things like lanthanum, cerium, yttrium, and also phosphorus, and we'd be convinced that these are inclusions of monazite and also xenotime, which are light rare earth and yttrium phosphates, respectively. And even then, okay, so we kind of know why our CO was funky. We don't know why they're there or what's causing them until textures like this became apparent. Now, this is a very elongated monazite inclusion, and it's nucleating within a micropore in our apatite. And to save you some apatite crystallography, that direction is parallel to the C-axis. And it turns out in apatite, the C-axis is the path of least resistance, and things can move around quite quickly. Because we're having micropores and we're having monazite, that's more or less parallel to the C-axis. Chances are this is actually a texture that's indicative of alteration. And in fact, that's the case, and this is what's causing it. This is the typical, I guess, or one of the methods you can produce monazite inclusions within your apatite. And this is what's called a fluid-mediated dissolution and reprecipitation reaction, which is a crazy, scientific term for a concept that everyone's familiar with. It's just hydrothermal alteration, where we have our initial magmatic apatite, subject that to a fluid, and fluid mobile elements mobilize. Now, the relative behaviour of these elements really dictates the products of our alteration. Mobile elements, things like sodium, chlorine, and silica, they'll actually mobilise out of our apatite grain. So it displays a bit of open system behaviour. The light rare earths, they're interesting because typically not thought of as fluid mobile elements, but they don't particularly like to be in apatite either. Apatite much prefers the mid-rare earths. And the fluid's got a bit of phosphorus in it. They'd love to crystallise monazite, because that's light rare earths are happy in a monazite crystal. That's exactly what happens. So a bit of fluid comes through, picks up a bit of phosphorus, our light rare earths jump out of our apatite into the fluid for a little bit, and then start to crystallise monazite. And particularly crystallise monazite within the cracks produced, or the permeability produced by the fluid. So happy days. Now we know what's going on, we know why. It's causing funky CL texture. But there's a problem here because we want to look at apatite from a magmatic context, and only this initial starting composition is representative of magma. Everything on this side of the reaction is not. That's not telling us about the magma. Don't care about it, or potentially don't care about it. And it's just going to cause us a headache. So the alteration that we're seeing is on such a fine scale that there's no way that you could avoid it in the microanalysis, particularly the laser ablation, because that's quite a big spot size. So instead of kind of fighting it, kind of embraced it and thought about what the alteration could tell us. So I took to the experimental petrology papers that work on this reaction. of which there were 54 different experiments, and the operating conditions you can see there. But the real story is told by these two pictures. In a very comparable result, this is a BSE image of the reaction products. Above we have natural grain from Mount Leyshon. The products of this experiment run with aqueous carbonic fluid at 300 degrees. Mimic Mount Leyshon like to a T, even to the point where we're having C-axis parallel monocytes. So we're pretty happy that this reaction under these conditions is representative of the same textural and chemical products we're seeing in Leyshon. And there's actually only two different experiments that replicated this. One of them is this one. The other one is with particularly acidic fluids. We know that the apatite alteration is telling us about the fluid regime under which they were altered. Now, pretty lucky at Mount Leyshon, there's a very well characterised fluid inclusion study, of which the results are summarised here. Now, the most important one from an economic perspective is this one, because this the fluid associated with the late dike is also a mineralising fluid. And particularly interesting is this fluid is the only one in the entire complex with appreciable CO2. And if we go back, we know that dilute aqueous carbonic fluid produces the same textures and chemical products that we're seeing in Leyshon. So it's a pretty safe bet that this fluid is causing the apatite alteration. So I guess take a step back now and see where that leaves us. On the bright side, the cause of our apatite alteration is also the cause of our mineralisation. So this is kind of the making of our first fertility indicator in and of itself. Okay, it's not an igneous fertility indicator, but it's telling us something. On the downside, now our microchemistry data set, particularly only in apatite, is I guess fraught with danger. We need to be careful when interpreting volatiles and also light rare earths going forward. And particularly interesting is these, I guess these aren't really recording the magmatic system now. Potentially the fluid immobile elements within apatite are. We've got to be careful with these guys. Okay, so here's some of the apatite data. Now, I went through the entire process of filtering the data to, I guess, only present the least contaminated analyses, of which this is the data that's displayed. And this is a graph of yttrium against manganese oxide. And they can be rewritten for the processes for which they're proxies for in apatite data. And in our case, that's dehydration for yttrium and differentiation for manganese. This does a really good job of pulling out our fertile porphyries. They're the ones in orange here. Everything else is barren, and the pink is our tin fertile site. So from this, we could suggest that our fertile porphyries at Mount Leyshon are water undersaturated. They're also fairly differentiated, which isn't really, I guess, groundbreaking. You can tell that just by looking at the core or by understanding, these are felsic rocks and high silica rhyolites typically are pretty fractionated and also pretty water unsaturated. So this isn't rewriting the book. Okay, let's have a look at the whole rock now. So these are, each different diagram represents a different sample. And the coloured analyses in each plot represents apatite data. And the grey diagram or grey curve is the corresponding whole rock. The fertile porphyries are on the bottom here in orange, and all the barren rocks are on the top, except for the pink one, which is tin fertile. And we can see some distinct differences, particularly in the fertile porphyries with this massive, not massive, but fairly big negative europium anomaly. Now, one of the things you'll notice is that there's a stonking big europium anomaly in the apatite, and it's not there in the whole rock. That really had me scratching my head. Now, europium is one of two rare earths that's polyvalent, which means it can occur as different, as more than one valence configuration. And europium can occur as 2+ or 3+. Now, when europium is 2+ in the magma, it can partition for calcium 2+ into the lattice of plagioclase. And that's, I guess, a classic interpretation of a negative europium anomaly within a mineral chemistry dataset. is that our apatites are crystallising at the same time as plage. And that's a cool that's a cool interpretation, and I agree that that's happening here. But what really stunned me was the lack of the European anomaly in the whole lot. Scratching my head, I don't know what's going on here. And what I put it down to pretty much was that, okay, apatite and plage are crystallising together, but the plage isn't fractionated away from our melt. In that the melt actually hadn't left anything behind, and it's all the plage that crystallised with apatite is then entrained within the magma. Also, an interesting, I guess, feature of the data here is that we don't have a spoon-shaped heavy rare earth. Now, these are the heavy rare earths under across here, and typically in porphyry copper systems, you'll see a big concave up spoon shape. We don't see that. In fact, the apatite has an inverse, if you like. And the spoon in the heavy rare earths is typically, I guess, ascribed to either the presence in the source region or the fractionation of minerals like hornblende and garnet. Now, we don't have that in Mount Leyshon, and actually we have the opposite trend of the apatite data, which would suggest that potentially apatite is one of the main hosts for the heavy rare earths. And this is, I guess, corroborated by the zircon rare earth, which has a much steeper slope in these really felsic magmas compared to things like the diorite, which has plenty of hornblende. So from this, we could kind of glean that these magmas haven't fractionated significant hornblende or garnet. Okay, so here's I guess the punchline, or half of the punchline to my thesis, is that these are our fertility indicators, or my fertility indicator scale, and that everything on this side of the dotted line here, these are processes that we can see happening at Mount Leyshon. But we're not sure if there's a direct link between them and fertility. In fact, I'm pretty sure there isn't. And everything on my side of the dotted line has a tangible link between a process that we can see in Mount Leyshon, and it also has a link to being a fertility indicator. So pretty underwhelming just with the apatite. And the only thing you can see is that the apatite's altered, therefore potentially fertile. But that's okay, this will change. So what about the zircon? Let's have a look at those. So these are, again, CL images of the zircon, and I did uranium-lead geochron and also trace element geochemistry. And the geochronology wasn't really a focus of my thesis. I was really interested in more in the fertility indicator side of it. But I guess it tells a cool story. In that Mount Leyshon is just like, you just get the feeling it's a super dynamic system. So between the first pulse of magma and the mineralisation is about 10 million years. So in that period, you have 3 pulses of separate individual magmas and associated brecciation and alteration and mineralisation. So I guess my work kind of confirmed that. We also were able to date some of the post rocks, which hadn't been done before, and kind of confirm that they weren't active during the mineralising period. And that's kind of where that ended. Okay, so looking at the zircon, this is a method called titanium zircon thermometry, which uses the thermal partitioning of titanium into zircon to estimate the magma temperature. And it's plotted against the decay-corrected uranium divided by titanium ratio, which turns out just to be a proxy for magmatic differentiation. Now, again, this isn't really groundbreaking. It's not really telling us something we don't already know. In the fertile late dikes, which are here in orange, they're pretty differentiated magmas and kind of low temperature. Which, they're a very kind of felsic rhyolite. Is kind of to be expected compared to something like the diorite up there in green, which is hotter temperature and less differentiated. You know, it's not quite groundbreaking, but it really is kind of the basis for more, I guess, further investigation, which is something like this. This is estimates of the magmatic oxygen fugacity, which is calculated using Bob Louse's calibrated oxybarometer. And this is some very interesting results. So on the y-axis, we have the FO2 content, which is humulus, I guess, and on the x we have the temperature. And the 3 lines on there, they're redox buffers, so they're, I guess, known points from which redox can be judged. And one of the things that's a really, I guess, jumps out at you is that the NNO buffer, which stands for nickel oxide, does a really good job of pulling apart our fertile porphyries from pretty much everything else. This is interesting because I put on the slide there, this result was more oxidised than we'd expect for an IRG. Typically, they're thought to be moderately oxidised to reduced, but it's less oxidised than the typical porphyry copper system. And for comparison, this is Tampakin, again for Boblaux, which is hotter temperature and also more oxidised than Mount Leyshon. Okay, so this is essentially the same data. Again, we're plotting redox on the y and temperature on the x, but this time redox is relative to the FMQ buffer. And on this side, this is a compilation of coal rock data from field 11. So bear in mind, a little bit of an apples to oranges situation. We're comparing magma to a rock, which is not necessarily correct, but it tells a good story. So the open squares in Phil's compilation, these are rocks associated with intrusion-related gold systems in the New England origin. And interestingly, if I squish the diagram and plot it on the same axis, you'll see that our magmas are pretty oxidised and our rocks aren't so oxidised. So from that, you could, I guess, infer that between the cessation of zircon crystallisation and the crystallisation of the entire rock, that there's a reduction somewhere. And that's important. That's one of the key findings that will become, I guess, a bit more apparent later. So this is data, again, using Boblaux's indicators. These are the 10 to the 4 times the europium anomaly of the normalised terbium is a proxy for melt hydration. And we can see interesting, I guess, trends in that the diorite magma in green is hydrating as it's cooling. And the late dikes don't do that. Gold fertile magma doesn't do that. And if we look at the hydration against redox, which is this graph here, we can see both the diorite is reducing and hydrating, and also the late dikes are as well. Now, in the diorite, this could be very, I guess, succinctly explained by something like the onset of hornblende crystallisation or fractionation of clinopyroxene. But in the late dikes, there's no CPX. That's we got to kind of invoke a different explanation. It's got to be a different cause for this trend, and that now. So if you'll remember, we've got an oxidised melt producing less oxidised rock. So there's got to be a reduction somewhere between the cessation of zircon and the crystallisation of the entire rock. So late in the magmatic history, we're reducing these magmas. Now, we also know that when we reduce them, we also hydrate them at the same time. And in my mind, the best way to, I guess, tick all of these boxes to reduce our magmas and hydrate them at the same time, late in the magmatic history, is to incorporate a bit of crustal material. And we can see evidence for that at Mount Leyshon, these little xenoliths of something. They're currently needly aggregates of chloride and sericite. But I suspect they used to be sediments. And this was really, I guess, a feature of the late dikes, which, again, may or may not make them fertile. But it is certainly an observation that we see there. Okay, so I guess this was the cherry on top. This is, I guess, the diagram that I produced at the end of my thesis, and a bit of a petrogenetic model for Mount Leyshon and how it came to be. Now, I haven't talked at all about the gold source, and it's kind of two reasons for that. One of them is that it wasn't really one of the questions I set out to investigate. And the other one is because it's already been kind of looked at by Mergelov. She does hafnium isotopes on zircons from Mount Leyshon and shows that the initial magmas, the early dikes, are a mixed signature between a crustal melt and a mantle-derived melt. And whether the gold's coming from the crustal melt, the mantle melt, or somewhere else, it's kind of inconclusive. Hafnium is not the right method to answer that question. And I guess it doesn't really matter, right? So like we have gold in the system, we know that. Where it's coming from, whether it's the crustal or the mantle melt, I would suggest probably the mantle melt, but without concrete evidence. We know it's there, right? That's a fact. And another, I guess, curiosity is again, this work from Roger Mustard's cropping up is, do we even need gold? We can concentrate gold in our magnets provided our magnets have the right evolution, the right petrogenesis. We can concentrate gold to economic levels without the need for a particularly rich magma to start off. I'm not sure, I don't have the answer to that, but it's an interesting tool. Okay, right, so we have gold in the magma somewhere, either as from a fertile source region, or it's being concentrated by the evolution. Either way, we need to preserve our gold budget in these magmas, either by favourable transport in the kind of fertile source theory, or by favourable petrogenesis in the no fertile source theory. One of the best ways to do this, to transport gold to the upper crust, is, as I mentioned, in oxidised melts that delays the onset of sulfide saturation, and as soon as that happens, it's nearly game over for all the chalcophile elements within your melt. Another way is through a particularly hydrous melt, but that's a little bit less efficient. And we know we have oxidised melts at Mount Leyshon, so this is working in our favour. Of course, there are geodynamic considerations, things like magma architecture and I guess avoiding magma pooling. In the case of IRGs, maybe that's a good thing for porphyries. And finally, the last thing that we must have is the exsolution of some sort of fluid and overall mineralisation. Now, in our case, it's an aqueous carbonic fluid, which is also altering our apatites. I've put here, could the reducing and hydrating evolution, does that have something to do with it? I'm not sure. But I guess it's food for thought. Okay, so here's the punchline. This is my take on accessory mineral fertility indicators from IRGs. And I've seen this all before, except for these newcomers here. And they're both offensive. They're neither here nor there. But really the reason for that is, as I mentioned, or as I alluded to earlier, is that just studying one deposit isn't convincing enough. Oxidised parental magmas, I suspect that's a key control. We know that's the case for porphyries. And I can see that also being the case for IRGs. And this reducing and hydrating the crustal assimilation, like a signature within our melts, is potentially another fertility indicator. But again, this is just because this process is happening at Mount Leyshon, A, doesn't mean it's critical to fertility, and B, doesn't mean it's applicable to other IRGs. So yeah, this I guess was some of my findings, and I guess sets me up quite well to talk about this work going forward. And I guess the key theme is that we need to look elsewhere. Mount Leyshon's told us this story, and if we look at more systems and it tells us a similar story, then we could be a bit more confident and start pushing some of these things over into the fertile field. A lot of the work that was done in the porphyry fertility indicator world was just based on volumes of data. Like there's a lot of known porphyry deposits. There's a lot of known barren arc rocks as well. They're in very well characterised tectonic regimes, all of which isn't the case for IRGs, which makes it a bit more difficult. And particularly studying one deposit, this one, it's not enough. It's not. We're not. Can't be confident that, as I mentioned, the processes that I see in the magmas of Mount Leyshon are applicable to other IRGs. And should we, continue to study these things, hopefully commonalities will appear between the petrogenetic evolution of something like Mount Leyshon against something like Kidston, which is another IRG in Queensland, and I think we can really develop this story. So hopefully I've been able to convince you that it's worthwhile, and we should go do more of it. Thanks.